Today we're going to focus on 5.4, which is an investigation of the logistic equation. The logistic equation is a differential equation that looks something like this. This is actually typically a more accurate depiction of population in the real world, because what ends up happening, like let's say we're looking at some sort of fox population or something like that. So at first, the fox population, like if we look, well, I can't cover that, but if you look up to here, it looks like it's exponential. So typically when we talk about populations, at first when they're growing, when there's no limiting factors, they grow exponentially, as we talked about, because initially their rate of change is going to be directly proportional to how many animals there are, okay? But what ends up happening is you have things like there's not enough food, there's not enough space, there's sort of a kind of a limitation on resources, so you get some sort of limiting factor that it starts sort of approaching, okay? So we end up with an inflection point here where it sort of switches from looking like it's exponential to then being the logistic equation. The logistic equation, differential equation, is not quite of that form that we talked about. It's dy over dt, not just ky, but we're multiplying it by this limiting factor here. And if you think about the way this is going to impact it, if we looked at this thing would grow without bound, because as y increases, nothing's going to slow it down. But what happens here is, as y gets closer and closer to this limiting factor, it's going to get closer and closer to 1. So this number is going to get closer and closer to 1. So this overall is going to get closer and closer to 0. So that's what's going to cause this thing, this rate of change, to then decrease. Okay, it's always going to be positive because technically it's never going to reach L. So it will continuously approach L as a horizontal asymptote, but it won't actually get there. Okay, so this is our differential equation. Now, one thing a little bit different than when we did the exponential was that we actually showed how to get from the differential equation to the solution equation, okay, the typical PERT formula. We're not going to do that this way in this. So here's, if we started to separate variables, we would get dy, let's go ahead and put this over y, and then 1 minus y over L. So I'd be moving these two factors over here, and then we're going to get equals k and then dt, and then we're going to integrate both sides. So obviously the right side, no problem to integrate. The left side uses a method called integration by partial fractions. We do not know that yet, so we will revisit this. I think it's, I wrote it down here, we'll see this in 7.5. So in 7.5 we'll revisit this idea, and once again we'll take a look at actually showing how we go from dy over dt to our differential equation. Oh, which is y equals L over 1 plus some other constant b e to the negative kt. Now, when I see something like this, really right away I can enter it. So for instance, if I get something like dy over dt is equal to some number, 0.2 y, and then 1 minus y over some limiting factor, let's say 10. I can go right to this solution curve, y equals 10 over 1 plus, we don't know b, and we won't know b until we're given an initial condition. And this would be negative 0.2 t. So as soon as I'm given that differential equation, that logistic differential equation, I can rewrite it as its solution curve, its solution equation, but I need an initial condition to solve for b. So once again, this derivation of going from this differential equation to the solution curve, we can do with exponential, but we can't do it with logistics yet because we need this partial fractions. Instead, in just a moment here, what I'm going to do is I'm going to do the opposite. Since we got to go this way, well, what about, since now we know what this is, can we confirm that if I take the derivative of this, I can get something of that form? And that's what I'm going to show you now. Okay, so once again, what we're going to do is we're going to now start with our solution curve y equals, and we're going to take the derivative of that and show that it's equal to dy over dt. You will be doing this as exercises with values plugged in. I will tell you the textbook takes a slightly different approach. It's really a preference thing. You do it the way you want to do it. So if I'm going to take the derivative of this, the first thing I really want to do is write this in a form that's going to be nice for me to take the derivative. So I'm going to write this with a -1 for an exponent here. So I'm not using quotient rule. You can use quotient rule, it doesn't make a huge difference. So then I get y prime is equal to, negative comes down, and we have to do chain rule. So this is going to be e to the blob, derivative of e to the blob will be e to the blob, but don't forget to take the derivative of the blob, so the derivative of negative kt will be negative k, so this will be negative k times b. Okay, now keep in mind, we want to kind of focus on what we're trying to get here. So we actually have something already if we keep this in mind, that this is y. So what I'm going to do here is I'm going to rewrite this thing as, bring out the negative k, and I'm going to get y prime, negative times a negative, of course, is a positive. I'll put the k out front, which I'll show you in a second, and the L. This I'll write as 1 over 1 plus b e to the negative kt, okay? And that's one of those. I have 2. Okay, because that's squared. And then we're left with the b e to the negative kt, all right? So now at this point, let me point something out to you. This is y, okay? And you can see we almost have the ky here, because what I can do here is I can bring this L up into the numerator here. Okay, so this is going to be L here. So now this is y. So I actually have this part already because I have k and then y. Okay, so I have y prime equals k and y, and now this thing right here, which I'll work on here in a moment. Before I work on this, what I want to do is I want to put this in terms of a form. Notice there's no b's here, so I have to replace this here. So I'm going to do a little algebra on this. Okay? Do a little algebra on this right up here. So what I have is I have this equation right here. So y equals L over 1 plus b e to the negative kt. I want to replace b e to the negative kt, because there's no form of that here, with y and L stuff. So I can multiply this on the other side. So I get y 1 plus b e to the negative kt is equal to, right, L. So now I can divide both sides by y. I'm going to need a safe room, so let me just do this with an eraser. So this is equal to divided by y. Okay, now I subtract 1. So I get b e to negative kt is equal to L over y minus 1. Okay, so now I'm going to replace this with this. So take a look at what I have. Okay, so I have this y. I have 1 over 1 plus b e to negative kt. All right, and now this I'm going to replace with this. So you can almost see we're there. Almost there. All right, now one last thing you'll notice is there's no b's here. I can now replace this thing with something in the form of y. Think about it. All I need is an L here. So what I'm going to do is I'm going to multiply top and bottom by an L. So if you let me do this, I'm going to multiply the top by L, giving me an L here. And then what's going to happen here, I'm going to have 1 over L. So notice, together that's just 1. So this I can now replace with y. So I'm going to make myself a new line here. Okay, so now at this point, what I see is I have y prime equals, this will be ky, all right? This is y, all right, but we're going to keep this separate because this is going to become part of this thing here. So this is y. Now this, I'm going to go ahead and distribute across. So look what happens here. I'm going to get the l's to cancel here, so I'll be left with 1 over y minus 1 over L. Okay? Now, we're in business. All I have to do is distribute this y, and you see we've got what we want. So distribute here, we get 1 minus, and then y over L, and we have confirmed this. Now, I want to point out to you, this was quite involved. I wouldn't expect you to do this without seeing it first, but now that you've seen it, you should be able to reproduce this. You'll do some exercises with this where they'll be giving you actual the values plugged in. So they'll give you an L, they'll give you a B, they'll give you a K, and they'll ask you to confirm the differential equation. Okay. Okay, so now we've confirmed that this is the solution curve to that differential equation. From here on out, we're going to be using these. Sometimes we'll use a differential equation, sometimes we'll use a solution equation to solve various problems. Some of them are going to deal with calculus. Some of them, like we did with the exponential growth and decay, are going to be outside sort of the scope of calculus, but using these equations. Okay, so just an example. So this isn't really a calculus equation, or we don't need calculus to get there, but obviously the notation is calculus. So find the logistic equation. Okay, so that's the logistic equation, the solution curve that satisfies the initial condition 0, 2 with the differential equation dy over dt is equal to 0.4y times the quantity 1 plus y over 10. For the most part, this is pretty easy. The first thing we point out is right away we know what L and K is. So this is our L, that is our limit. This thing will limit to that value, and this is our K. So that's really easy. So right off the bat, I'm going to have y is equal to 10 over 1 plus b, and then e to the negative 0.4 t. Okay, now if they don't give me initial condition, that's the best I can do, but here you can see they're giving us initial condition, so I'm going to be able to solve for b. So I'm going to plug in our initial condition, so that will give us 2 equals 10 over 1 plus, and then b times, and then realize that it doesn't matter what's going on here. This is e to the 0, which is going to be 1, so we're going to get 2 equals 10 over, and then 1 plus b. So this is just going to be b is equal to 4, right? So that's 5. Yeah. So now we put it together. So pretty easy stuff here once we've gone through the calculus. So dy over dt is equal to, no, I'm sorry, I'm doing the solution curve. You already have that. So y equals 10 over 1 plus b, no, not b. We found that b is 4. Okay, and this will be e to the negative 0.4 and then t. So there is my logistic equation, my solution to that differential equation. They might have you confirm this, so we should be able to go through the process I showed you earlier where we could take the derivative of this, do some algebra here and get it to look like that differential equation, but we don't need to do that here. The last thing I want to do is confirm that we limit to 10 for the limit as t goes to infinity. So as time goes on, we limit to 10. So let's look at this equation here and just show that that's what's going to happen. Now this is a negative exponent, so I'll show this as a nested fraction, and this sort of tells you exactly what's going to happen here. Because as we go to infinity, clearly the fact that it has a 0.4 is meaningless for large numbers. 4 over something getting closer and closer to 0. This thing will go to 0, so we're left with 10 over 1, which is equal to 10. So we're clearly seeing this limit of 10 as we go to infinity. Okay. Next thing I'm going to show you is how we find the inflection point, which on the front end, once again, is going to involve a lot of calculus, like confirming, taking this and getting there. It's going to be a lot of calculus, but ultimately, once we get there, it's going to be pretty easy. Okay, let's return to our original graph. So once again, we have our solution curve, we have our differential equation. If you look at the differential equation here, we have, if we look at the slope fields, and you'll see these in the book, I'm not going to draw them, but you have a bunch of hashes moving to this from the bottom, getting closer and closer. You can almost see the shape of the solution curve. And then we have a bunch of hashes coming from the top. If we look at L here, typically we're not very concerned if Y is greater than L. If Y is greater than L, we will have something that will push this down towards the horizontal asymptote. So if you think about what's happening there, if we plug in values where Y is greater than L, you're going to end up with a negative here, right? So what's going to happen is this is going to push down. But once again, it's going to get closer and closer to 1, so we still have that horizontal asymptote. What we're generally talking about when we do these is we're going to have some Y that's between 0 and L. If Y is actually equal to L, we just have a horizontal line, right? Because you'll get a slope of 0. So that's, once again, kind of trivial. So you're going to have some initial condition, and then we have sort of this exponential growth. And then at some point, this thing has an inflection point, and we go concave down towards the horizontal asymptote. What I'm interested in finding is that inflection point, okay? So the way we're going to approach this is like we always approach inflection points. We are going to take the double derivative and set it equal 0. Once again, the math here is quite involved. I wouldn't expect you to reproduce it, or I wouldn't expect you to do this, but I would expect you to be able to reproduce this. I want to point out to you, we already have the first derivative, so we just need to take the derivative of this. So d squared y over dx squared. Now if I take the derivative of this, I'm going to use product rule. Derivative ky will be k, but don't forget we have to use chain rule, so we'll say y prime. Okay, copy this down. Plus, now switch it. So we're going to copy down the ky. Okay, now we're going to take the derivative of this. So the 1 is going to go to 0. This is going to leave us with negative, let's call it 1 over L, and then times y prime. We can, I don't know ultimately what it's going to be nicer. It really doesn't matter, so we'll deal with it. Y prime, we want to know when that's equal to 0, okay? And that's what we're trying to find here. All right, so now notice we have these y primes, so we want to substitute it with what we know y prime to be. So d squared y over dx squared. I should probably confirm. I did this earlier to make sure I wouldn't make a error. Okay, looks good. So we're going to plug in the y prime. So this will be k. Notice y prime, we're going to have another k. So this will be k, and then y, 1 minus y over L. Then we have this quantity. Plus ky, and this, negative 1 over L, okay? And then once again, y prime, we're plugging this back in. So we'll have ky, and then 1 minus y over L, okay? Now, we want to know when that's equal to 0. We're getting old school with this. What we're going to end up doing is an old trick we learned like way back in Algebra 2. We're going to do factoring by grouping. So we're going to look for all these sort of GCFs I can get out of here. So maybe let's organize this up just a little bit. So let me point out here that this is k squared. Okay, and then here we can call this k squared as well and y squared. Okay, let me put this all together. together. And don't forget the negative 1 over L. Okay, so I just condensed that down. Now, if I look at this, what I can do is I can factor out a k squared y, 1y, and then one of these quantities, right? So this is equal to k squared y, 1 minus y over L. Okay, so I'm bringing this out here. Notice I have it here, k squared y, so I'm going to be left with 1y here, and then 1 minus y over L. So inside, that's going to leave me with, this whole thing factors out, the quantity 1 minus y over L, plus, this still leaves me with a y, remember? And this whole thing will factor out, so we're left with, well, let's call this negative y over L equals 0, okay? So, first of all, these things we don't have to worry about because, okay, so keep in mind what we're doing here. We're doing the zero product property. So we have this term times this term times this term equals 0. These two terms we don't have to worry about because if y equals 0, we're just talking about a horizontal line. So we're not concerned with y equals 0. Also, if y equals L, if y equals 0, we're just going to be on that line. Y equals L, then what we're going to get is 1 minus 1, which is 0, so that is just a horizontal line, L. So I don't need to concern with this. We're talking about 0, or y being between 0 and L. So all I have to focus on is this last thing. So 1 minus 2y over L is equal to 0. So easy to solve here. So this will be 2y, and then that's equal to L, so y is equal to L over 2. So a really easy result here. So what we find out from this, and it doesn't matter what L is, as long as we're starting with initial condition between 0 and L, this inflection point will occur at L divided by 2. Now, some of the time, or part of what we're going to focus on, typically if you think about it, we're not interested in the dependent variable, the y, being half of the limit. Typically we're interested in the time. So the algebra comes in, you don't have to go through this thing again if they ask when the inflection point occurs. You know that whatever that limiting factor is, then the inflection point will happen when the y is halfway there. What we're going to have to find is the t. So I'll show you an example of that. Okay, so let's return to the example I did before we did the inflection point. So once again, we have this differential equation. We found that the solution curve y equals, for the initial condition 0, 2, was this equation right here. Now what I'm going to do is I'm going to find the time when we have our inflection point. So our limiting factor is L. So we know that this starts at 0, 2, okay? And we have 10. So we know that this thing's going to have the typical logistic sort of shape to it. We want to know the time that we get the inflection point. And what we learned from doing the calculus before, and from here we don't really have to do the calculus, we know that this is always going to be half. So our inflection point will happen when y is equal to 5. So y is equal to 5 is going to be our inflection point. Okay, half of L. So really from here it just becomes a matter of doing some algebra. So we're going to enter 5 is equal to 10, 1 plus 4e to the negative 0.4t. Okay. Now we have to find t. I'm going to go ahead and multiply this quantity on the other side. 1 plus 4e to the negative 0.4t. So I'm multiplying it over here. Let's divide both sides by 5. That will give us 2. Okay. Subtract 1. So 4 is e. Negative 0.4t is equal to 1. So now we have e to the negative 0.4t is equal to 1/4. And as always, folks, I would suggest only doing one calculation at the end. We want to get this thing down, so we're going to ln. So negative 0.4t is equal to ln of 1/4. Okay, so our t will be ln of 1/4 divided by negative 0.4. So let's calculate that. And what we get is 3.4657. So our t here is going to be 3.4657. So we don't have to do any calculus there to get the inflection point because we know it's going to be half that limiting factor. Okay. So once again, the big focus for this section is solution curve right here, differential here. One of the things that you're going to see in this section is a lot of problems that aren't directly calculus. Obviously, these come from calculus, but you're going to be answering questions like find an inflection point, also finding values like here's the L, here's the K, can you reproduce this, can you get this given the initial condition. So kind of like what we saw in the exponential growth and decay, sort of working behind the scenes is the calculus, but we'll be answering questions that aren't directly calculus. So that is section 5.4, the logistic equation.